We learned in the beginning of this semester that you can solve equations by writing matrices of coefficients and doing these row operations, right? So some books call it elementary operations, some books call it Gauss operations. But these row operations were performed to reduce the matrix into a row-reduced echelon form, and that gave you a solution, right? So if you have done the homework, you probably remember that as well. But today I want to show you that you can do something similar with matrix multiplication, and also I want to discuss what it means for the determinant. Okay. So first, take the identity matrix and let's try performing some of the row operations. What row operations do you remember?
Scale.
Scale. You can multiply any number, a non-zero number to any row, okay? So you can multiply, say, R1 by 2. Okay? Then it gives you 2, 0, 0, 0, 1, 0, 0, 0, 1. Okay? Okay. What's another operation you remember?
Swap.
Swap two things. So you can swap, say, the row 1 and row 2 could be swapped. And then that result will be 0, 0, 0, 1, 0. And then 1, 0, 0, 0, 0, 1. And that remains just one more. What else?
Pivot.
Huh?
Pivot.
Pivot, okay. What's that?
It's multiply negative.
Multiply, yeah.
Is when you add one row multiplied by a number.
Yeah.
Right. So you take some multiplication of one row and add to another one. So for example, you can take 3 times R1 and add it to R3, replacing R3. So if you do that, 1, 0, 0, only the R3 will be changed because you're taking 3 times this row and adding it to the third, it will be 3, 0, 1. Now, surprisingly, if you take these matrices, if you take the identity matrix and apply these row operations, and you obtain another set of matrices, and this is only true for square matrices, okay? If you have these square matrices, you can multiply this to another matrix to have the exact same effect. So let me explain what I mean by that. So think about you have A, B, C, D, E, F, G, H, I, something like that. Maybe I should have written A, B, C. It's okay. So some matrix, okay? Just observe what kind of operation is done. This times this gives you what? This times this. 2A, right? Plus 0, right? Okay, now this times this. It's a little noisy. Okay, back to this. Okay, so if you do 2, 0, 0 times D, E, F, you get 2D. And then same thing, 2G. But then when you multiply 0, 1, 0 with the ABC, what do you get?
B.
B, D, F, just E, H, C, F, I. So what happened? What happened going from here to there? The first row got multiplied, it doubled, right? Okay. Now let's try to see what happens if I multiply 0, 1, 0, 1, 0, 0, 0, 0, 1 to the same thing. I'm not going to write this. What would you get? If you do this times this, okay, ABC, what do you get? B, right? Yeah. Then DF times 0, 1, 0, you get E. And GHI, this times this gives you H. And this times this gives you A, D, G, C, F, I. So what happened? The first two rows got changed. Okay. No. The last one is 1, 0, 0, 0, 1, 0, 3, 0, 1. Okay, if you do this times this, well, nothing happens. It's just A, right? D, E, F times 1, 0, 0 just gives you D. And then G, A, G, H, I gives you G. It will be same thing, B, E, H. But this is, the last one is the one that we have to focus on, right? 3, 0, 1 times A, B, C. What's that? 3A, 0B, 1C. So what do I write? 3A plus C. And then when you multiply this with this, is 3D plus F, right? And then it'll be 3G plus I. So what happens here? What happened? It's the same operation, right? So whatever you do to the identity, if you multiply on the left, it happens that you end up with the same kind of row operation on the other matrix. Now, if you multiply not on the left, but if these two things are switched, then you'll observe that now those are column operations. So you can try that as well. Right? So if you do this times, if these two things are switched, then instead of the first row being doubled, you'll see that the first column will be doubled. And that's because we know that matrix multiplication is not commutative. Right? So that's what happens. Right? Okay. Now, what does this have anything to do with determinants? Well, the reason I'm bringing this up is because this kind of tells you what's going to happen to the determinant when you do any of these operations. So probably the most important operation, the most important property of the determinant is that determinant of A times B is same as determinant of A times determinant of B. I didn't prove this, but I kind of explained why this is true. That's because matrix multiplication is composition of functions, right? Where determinant keeps track of what's the ratio of the change of the area or the volume, right? So if B was applied to make the image double, and then A was applied to make the volume or area triple, then if you apply it together, you will get 6 times the original one. So that's what this means. So even though I didn't prove it, it kind of makes sense why it should be the case. Okay? See, one thing that you observe in mathematics is that people try very hard to come up with the right definition of something. They were like, so think of the moment when people didn't know about matrices and they had to invent this matrix multiplication. Perhaps they first thought that matrix multiplication is simply just multiplication of individual numbers. But then that doesn't have any good properties. But then people think of this more and they say, oh, maybe matrix multiplication should be mimicking what happens when you compose two linear functions. And that they come with a totally crazy type of multiplication that if you explain to somebody who's never seen it, like that's crazy. Why would anyone do that kind of calculation, right? But because you've defined it correctly, then all kinds of natural things happen, like this one. Right? Nice properties. Okay? And by the way, I want to add that A plus B, this doesn't go well with the determinant. This is not the same as this. You wish, but it's not true. Okay? So that's something to remember. Right? And then there's something I also said last time, which is K times A is not K times that, but rather K to the nth power times A, where A is n by n matrix. Okay? So these are some things that you should know. Okay, but what I want to do is to think about the determinant of those matrices on the left. So 2, 0, 0, 0, 1, 0, 0, 0, 1. What is this determinant? Well, let's do row expansion like how we did last time, right? So it's 2 times what? 2 times 1, 0, 0, 1, right? But then the rest are 0, so the row expansion just stops here. What's the determinant of 1, 0, 0, 1? 1, right? AD minus BC gives you 1. So this is 2. And then think about the following. If I call this matrix as A, okay, then what's the determinant of 2, 0, 0, 0, 1, 0, 0, 0, 1 multiplied to A? According to this formula, what do we know? It should be the determinant of 2, 0, 0, 0, 1, 0, 0, 0, 1, right? Times the determinant of A. And we know that this is 2, so it must be 2A. And if this number was some random k, what happens then? That was just k, right? So this means that if any one row is multiplied by a number k, what's the result of the determinant? What happens to the determinant if you took a matrix and just multiply one row by k? That k will come in front. That's the proof. Okay? I mean, it's almost the proof. I didn't like write this down formally to make it a proof, but it just makes sense, right? And that's why if you had a k times a in general, this comes out as k to the n a. Can somebody explain why? What does this do? K times a. K times a means what?
The whole matrix gets.
The entire matrix, that every row is multiplied by k, right? So when each of the row k's are coming outside, what happens? How many times are you coming out? Making it come out? N times, number of rows. So n is the number of rows. That's why this is true. Right? Okay? All right. Since we just realized that that's something worthwhile doing, let's also do this one. What's the determinant of this? We actually did it last time. This is what we call the transition, right? Do you remember the determinant of this one? Huh?
1? I'm
No.
sorry, no, negative 1.
Negative 1, yeah. If you do the determinant of this, it's negative 1. So this second line actually says that if you interchange two rows, then the determinant is negative of itself. Okay? So that's a property that I said on Monday without really proving, but now that's the proof. Okay? The reason, I mean, all the other properties that I talked about just really comes from here. So if you accept this, then everything else follows. So if two rows are interchanged, and this is same for the columns as well. As I said, if you switch these two around, then now the row operations become column operations. So if you switch two columns, then again the determinant will be negative. Okay? Right. Now the mysterious thing is this third one. Let's try to calculate the determinant of this thing. Determinant of 1, 0, 0, 0, 1, 0, 3, 0, 1. Now, if you do a row expansion here, you get 1 times what? Say 1, 0, 0, 1, right? What's that? 1. Oh, so this 3 didn't do anything at all. Yeah. If you do the shortcut that I told you last time, which is, this only works for 3 by 3, by the way. If it's 3 by 3, there's a shortcut that you learned in Calc 3, which is to copy the first two columns, 1, 0, 3, 0, 1, 0, like that. And then you take 3 you get triplets of diagonals. Okay? You multiply these, add, and then you subtract these other triplets. So 1 times 1 times 1 gives you 1, but all the other ones multiply to 0, right? And then these all have zeros in there, so that's also 0. So you end up with 1 minus 0, which is 1. So you can do it that way and still get 1. And what does that mean? That means that if you have a matrix, you take a multiple of one and add it to another, what happens to the determinant? Stays the same, because that is 1, right? Yeah. It doesn't change. Okay? So now we can write these as the summary. Okay, so summary of observations. A, multiplying a row by k makes determinant what? Makes determinant multiplied by k. Right? Okay. B, interchanging any two rows makes determinant what? Huh?
Inverse?
Not inverse, you don't say inverse. What happens to determinant if you switch two rows? Negates. Okay, so determinant be the negative of itself. Okay. All right. And then C. Adding any multiple of one row to another does what to the determinant? Another row, what happens?
No.
Yeah, does not change the determinant. Okay, so these are 3 properties that you can figure out by thinking about these elementary operations, elementary row operations.